Hello everyone, welcome to Neso Academy. We are learning theory of computation, and in the previous lecture, we have understood what is an NFA, and you already know what is a DFA. So now in this lecture, that is DFA versus NFA, we are going to see comparisons between deterministic finite automata and non-deterministic finite automata. So the topic for this lecture would be DFA versus NFA. And we are going to understand the major differences between DFA and NFA on the basis of several properties. So the first property is determinism. In a DFA, the next state is uniquely determined for every state and input symbol, which I have already told you that in case of DFA, the next state is unique. For every current state, we have one unique next state. Like in this diagram, you can see for the state Q0, we have only one unique next state on input symbol A. And for the current state Q0, we have only one next state Q2 for the input symbol B. That means the next state is uniquely determined for every state and every input symbol. But in an NFA, the next state is not uniquely determined. Multiple possibilities may exist. In NFA, it is not necessary that for every current state you will have only one unique next state. Like in this diagram, you can see for the current state Q0, we have two next states, Q1 and Q2, for the same input symbol A. That means multiple possibilities may exist in NFA. Let's see the next property. Number of transitions. In DFA, exactly one transition must be defined for each state and input symbol. So in case of DFA, there is exactly one transition for every state and input symbol. Like in this diagram, you can see for the state Q0 and input symbol A, you have only one transition. For the state Q0 and input symbol B, you have exactly one transition. So in case of DFA, you have exactly one transition for every state and for every input symbol. Not less than one, not greater than one. But in NFA, 0, 1 or more transitions can be defined. That means in case of NFA, we can have 0 transitions, we can have 1 transition, we can have more than 1 transitions. In this diagram, you can see for the state Q0, I have 2 transitions for the same input symbol A. For the state Q1, I don't have any transition for input symbol A. For the state Q2, I have only one transition for input symbol A. That means there can be 0 transitions, there can be 1 transition, and there can be more than 1 transitions also. Let's see the next property. Computation paths. Now what is computation path? The path for processing an input string in an automata is called as computation path. And DFA has only one computation path for a given input string. That means in case of DFA, for a given input string, we have only one processing path. Like in this diagram, if you take an example of input string AB, let's see how can it be processed. The input string AB can be processed like A, B. Now, can you find any other computation path for the same string AB starting from the initial state? No. There is only one computation path for the string AB, and that is A, B. There is no other computation path. So we can say that in DFA, it has only one computation path for a given input string. But NFA can have multiple computation paths for the same input string. Like in this diagram, you can see, if I take the same input string AB, first computation path is A, B, and the second computation path is A, B. So for the same input string, I can have more than one computation path, but it is not necessary. It can be possible in case of NFA. The fourth property is transition function. DFA uses a transition function of type delta Q cross sigma gives us Q. While NFA uses a transition function of type delta, q cross sigma gives us 2 to the power q. So I have explained you the 5-tuple representation of both DFA as well as NFA. And in the 5-tuple representation of DFA and NFA, only one element was different, and that was the transition function. In case of DFA, we have the current state, we have the input symbol, and we have only one next state. While in case of NFA, we have the current state, we have the input symbol, but there is set of next states. That means more than one next state can be possible in case of NFA. Next property is epsilon transitions. DFA does not allow epsilon transitions, while NFA may allow epsilon transitions in case of epsilon NFA. So I have told you multiple times that in case of DFA, every transition should be triggered by an input symbol. There cannot be any epsilon transition or null move in a deterministic finite automata. In case of NFA, it may allow epsilon transitions, but only in the case of epsilon NFA. So if I talk about the regular NFA, it does not allow the epsilon transitions. But there is a special type of NFA which is called as epsilon NFA, in which the epsilon transitions are allowed. Next property is acceptance condition. DFA accepts a string if the single computation path ends in a final state. So I have just told you that in case of DFA, we have exactly one computation path for a particular input string. So if that one computation path reaches the final state, then our string can get accepted by the automata. Like in this case, if I take the same example of the string AB, it will be processed like A, B. So the computation is ending at final state. That means AB will be accepted by this DFA. NFA accepts a string if at least one of the possible paths reaches a final state. In case of NFA, I have told you, there can be multiple computation paths for the same input string. Like if I talk about the same input string AB, first computation path is A, B, and the second computation path is A, B. Fortunately, in this example, both computation paths are reaching the accepting state. So the string AB will be accepted. But according to this point, even if one computation path reaches the accepting state, then also the string will be accepted. So in case of NFA, if at least one of the possible paths reaches a final state, then also the string will be accepted. Our seventh property is ease of design. DFA is comparatively harder to design for complex patterns, which you already know. In case of DFA, you have various constraints, like for every current state, you can have only one unique next state. You have to complete all the transitions for all the input states. But in case of NFA, there are no such restrictions. That is why DFA is comparatively harder to design for complex patterns. But NFA is easier and more flexible to design. Like you can see, in NFA, you don't have to complete all the transitions. Non-deterministic behavior is also allowed in NFA. And it is to be noted that when you will make an NFA, it is not necessary to complete all the transitions. You will only make the sufficient and necessary transitions that will recognize the given language. But in case of DFA, we need to make all the transitions to make it a valid DFA. Our last property is conversion. Every NFA can be converted into an equivalent DFA, but every DFA is already NFA, so no need of conversion is there. That means every NFA can be converted into a DFA. If you have an NFA, you can convert it into a DFA. And this topic is very important. There is a proper algorithm to convert NFA into DFA, which we will study in the upcoming lectures. But every DFA is already an NFA. This I have told you in the previous lectures, that every deterministic finite automata is also a non-deterministic finite automata. So there is no need to convert a DFA into NFA. So these were the major differences between DFA and NFA on the basis of total 8 properties. Now before ending this lecture, let's see few important points on DFA and NFA. So the first important point is DFA and NFA have equivalent computational powers, which means that the computational powers of both DFA and NFA are same. It is not like that DFA is superior to NFA or NFA is superior to DFA. If a DFA can be constructed for a language, then an NFA can also be constructed for the same language, and vice versa. So if you are given with a language and if you are able to make DFA for that language, then making NFA is also equally possible for the same language. And if you are able to make an NFA for that language, then making DFA is also equally possible. And that's what we mean by DFA and NFA have equivalent computational powers. Let's see the next point. Both accept the same class of languages called regular languages, which means both DFA and NFA accept the same type of languages called as regular languages. And we will understand more about regular languages in our upcoming lectures. So these were the 3 important points on DFA and NFA. And in this way, we have completed our topic DFA versus NFA. This was all from my side for this lecture. Thank you, and I'll see you in the next lecture.